Hey everyone, here we go. We are now going to do another one of these videos. It's been a while, but we're going to make one. So, we're looking at higher tier combined science paper 5, which is the second of the two higher tier chemistry papers. Now, it says the student used the apparatus in figure 1 to investigate the rate of reaction between a metal and dilute hydrochloric acid. Now, this picture tells you lots of information about it, such as it makes hydrogen. We've got a 250 centimetre cube measuring cylinder here, a trough with water, and obviously our metal pieces and hydrochloric acid. We've also got a graph showing the rate of reaction. Now, it says, and I quote, name a piece of apparatus which would be better to measure the volume of gas instead of the 250 centimetre cube measuring cylinder. Now, we've got to say here, obviously, we're going to use a gas syringe. Okay, now a gas syringe is a piece of equipment we used. We have some of those and we use them, and the reason for this, quite simply, is it has a higher resolution. Now this means smaller scale divisions. Okay, so essentially instead of that 250 centimetre cube measuring cylinder with the big gaps between these, there's lots of little bits in between them, lots of little divisions, and therefore you can measure it better. Okay, you can measure it more accurately. Number 2 said, calculate the mean rate of production of hydrogen over the first 90 seconds in centimetres cubed per second. So, first of all, obviously, we've got the time, which is 90. You need to identify, as you can, quite straightforwardly, okay, how much 90 seconds is. Okay, now obviously 90 seconds is a minute and a half, so it's around about here. Obviously, you do this better on an actual graph. It's very hard to do this with my pen. And if you read up and across, you will see that it's actually about at 29. So the volume here would be 29. Okay, so that's the volume of gas produced divided by, that was a terrible line, the time, which is, as it tells you, 90 seconds. Okay, so you've read the volume of 90 seconds at 29 centimeters cubed. That's 1. You've got the rate there. You've got the equation, which says, you know, you've filled in the volume produced divided by the time, and then finally you simply use your calculator to work this out, which is 0.3222 centimeters cubed per second. Okay, so 1 mark for that, 1 mark for the formula, and 1 mark for the answer. Okay, now it says, and I quote, the student measured the volume of gas for 10 minutes. State why the measurements could have stopped at 9 minutes. Well, if you look at 9 minutes here, this point here, you can see the line is already horizontal. What does the horizontal line mean? What does that mean on the graph? It means, okay, the volumes were constant. Okay, that means, obviously, as we know, the reaction has stopped. There's no further reaction. It says the experiment was repeated, but with acid of a higher concentration. The rate was faster. Explain why. Now, obviously, if you've got a higher concentration, what you then have is more particles present. Okay, you have more particles. Okay, so you then have a, that's a terrible H, a higher frequency of collisions. Okay, so you have a higher frequency of collisions. 2 marks there, lovely. Now, it says, a student suggests other ways of increasing the rate of reaction. Which one is correct? Okay, if you use a lower temperature, so this one, a lower temperature, it's going to go slower. Using a larger trough, okay, or a smaller flask isn't going to do anything. So the answer there is D, because if you have a powdered form, you have a large surface area, and it will be faster. Now it says question 2 is, this question is about gases. When sodium is added to water, hydrogen gas is produced. What observation shows? Now this is obviously bubbles, but how do you say bubbles in a fancy way? You say effervescence. There we go. So we're going to cross B. Some damp litmus paper is placed in the gas. It's bleached. Which gas bleaches damp litmus paper? Now you need to know these 4 gas tests. Okay, you do. Now, carbon dioxide, obviously, to test for that, lime water turns milky, cloudy. Chlorine bleaches damp litmus paper. If you want to be technical, it's damp blue litmus paper. Hydrogen, a lit splint gives a squeaky pop, and oxygen, a glowing splint will relight. So it asks you which one bleaches litmus paper. It is chlorine. No magic trick there, you just got to know it. Okay, now this next one says, when calcium carbonate is heated, it decomposes. 5 grams of this, okay, so 5 grams of this is heated, and you end up with 2.8 grams of this. Now, obviously, if there's 5 grams on the left, there's got to be 5 grams on the right, because all of those 5 grams will be on the right in some form. So if only 2.8 is made, very simply, you very simply do 5 minus 2.8, okay, to find out the mass of this would be essentially 2.2, but it says give it to 3 significant figures, so we'll say 2.20. There you go. Now, if you don't give it 3 significant figures, yeah, you'll only get 1. Now it tells you there to do it, so just do it. Nice. Okay, first row of, hang on, I'm moving a page accidentally. Hopefully I haven't messed all that up. Never mind, it'll be fine later. Now, first row of questions done. Let's move on to the second row. It says a diagram of an atom of helium is shown in figure 3. Explain why this is inert. Well, helium obviously is a noble gas, which means it has a full outer shell. That shell is full, okay, which means it does not gain or lose electrons. It does not gain or lose electrons. It doesn't need to do it, okay, just doesn't do it, because it's full, it's stable. It says helium is used to fill balloons. State one property of helium, apart from being inert, that makes it suitable for filling balloons. Well, it's less dense than air. You know, we've all had balloons filled with air. They just fall. They're all right, but actually a helium one's far more fun, and you get to play with the helium afterwards and make your voice very, very squeaky there, which is very nice. Now, oxygen gas has the formula O2. Calculate the number of oxygen atoms in 3.5 moles of oxygen gas. Now, first of all, you've got to remember that obviously oxygen gas is O2. Therefore, what you'll actually end up with there, okay, is 3.5 times 2. That will be essentially 7 moles of O. Okay. You then say 7 times Avogadro's number, Avogadro's constant, which tells you there 6.02. If you're old like me, you'll remember it's 6.023, but don't worry about that. Use the value they give you, and you times that. So obviously, it's not times, it's 6.02 times 10 to the 23. Okay, because it's standard form. Okay, this gives you a final answer of, I'll write over here, 4.214 times 10 to the 24, my calculator says to me. So there we go. So 1 mark, obviously, for recognizing that it has 7, and 1 mark for timesing that 7 by 6.023 times 10 to the 23. Good. Question 2 down. Let's move on to question 3. Question 3 says, it gives you some information about the components of pollutant exhaust gases from the engines of 2 different vehicles. Give 2 ways in which the data in figure 4 shows that a diesel engine is more damaging to the environment than a petrol engine. Right, so basically, why is diesel worse? Okay, so here, it's better. Here, it's better. Okay, here, also, hang on, no, nitrogen oxides, it's worse, isn't it? That's worse there. Particulates, okay, it's worse. It contains 0.046 instead of 0.006. Now you might think, hey, 60 is a bigger number than 46, but you've got to watch the number of zeros there. Okay, so basically it releases more nitrogen oxides and more particulates. Lovely. Now, it says then explain, so you're going to have to talk about it, why the diesel engine is less damaging. Now, I would say, okay, you can basically talk about 2 fun things here. I would either talk about carbon dioxide, that one, or sulfur dioxide. I always like to talk about sulfur dioxide. we'll say it gives out less sulfur dioxide. I'll shut it every time I use an F, but I will. So less sulfur dioxide. Okay, now you've got to explain why that's bad. You get 1 mark just saying less sulfur dioxide. But why is sulfur dioxide bad? Well, it causes acid rain. Okay, sulfur dioxide causes acid rain. Now, which statement about the members of the alkane homologous series is correct? Okay, so you've got to write that. Do they show trending chemical properties? Well, they all have the same chemical properties. They're in homologous series. Their boiling point decreases as the molecules get larger. That's wrong. It's the other way around. The molecular formula of neighbouring compounds differs by CH3. Ooh, cheeky. Very close, but it's actually CH2. And finally, D. The viscosity increases as the molecules get larger. That is the true one. So we'll go with D. Now, it says, which of the following hydrocarbons belongs to the same homologous series as octane, C8H18? Now, you'll remember that to work out the formula of an alkane, it's CnH2n plus 2. That means whichever one there, essentially, we're looking for something that isn't double the number of carbons or less, less than double. So that's 4, 6. That's not it. 4 and 8, that's double. 4 and 10, does that work? So 4 times 2 is 8, plus 2 is 10. So C is the answer there, okay? Just finally go. C4H12, no, that doesn't fit our general formula. So we're good. Right, oh, look at this. Write the balanced equation for the complete combustion, okay, of octane. This is going to be fun. C8H18 plus O2, okay? Now, you get a mark just for saying that, okay? It burns and reacts with oxygen. Now, you then get a second mark for writing CO2 and H2O, okay? Second mark for that. So even if you can't balance it, you can get 2 out of the 3 there. Now, let's throw some balancing in there really quickly. Now, you've got 8 carbons over here. So let's do 8 carbons on the right. You've got 18 over here. So you're going to go 9 H2O. You've then got to do some maths, some adding up. So 8 times 2, obviously, is 16. 9 plus 1, 9 times 1 is 9, 16 plus 9 is 25. So that means we need 25 oxygens on this side. Now, what you can do is have 12 and a half. Brilliant. Okay, or if you would rather use whole numbers, simply double everything. Go with 2, go with 25, go with 16, and go with 18. Okay, you can have, as you know, half a mole of one of these things. It's because these are moles. Okay, sometimes they like whole numbers, sometimes they don't. If all else fails, halves are perfectly allowed. They can be any decimal you like. You can have 3.12 moles of oxygen if you want. Okay, the elements in group 7 of the periodic table is known as the halogens. Name the halogen that's in period 4. Here you'd look at your periodic table and you'd write the name of the one that's in period 4, which is bromine. Okay, essentially it's the 4th one down. Explain why chlorine is more reactive than iodine. Oh, what a beautiful question. They always ask these. Now, you just need to say, okay, you can either go one way or the other. Okay, now I'm going to say, okay, that in chlorine, okay, the outer shell is closer. Okay, in chlorine, the outer shell is closer. That means the force between the positive nucleus and the negative electrons, I'm going to wander off the paper here. Don't do this, especially right on the table at this point. Is stronger because they're closer. Okay, therefore electron gained more readily. Lovely. Now C says you're going to react sodium with chlorine. What are you going to make? Sodium chloride. That's what you'll make. Beautiful. Next, let's scroll down to, I might zoom out of it, make my life a little bit easier. That doesn't make my life easier at all. Anyway, we've got 2 rows of questions left, so let's get cracking on those. It says, sodium also reacts with bromine. Write a balanced equation for the reaction between sodium and bromine. So let's do this. So we've got Na, okay, plus Br2. That's going to give you NaBr. Okay, now I've got to balance this, so we've got 2 bromines here, so we need 2 over here, so you need a big 2 in front of that to give you 2 bromines. We've now got 2 sodiums, you just need a big 2 there, and there we go. That's sorted. Now in another experiment, a student adds colourless sodium bromide solution to chlorine water. What will happen then? Obviously, the chlorine will displace the bromide from sodium bromide to make bromine, so it would turn orange, simply put. Nice. Now, the order equation for the reaction between sodium bromide and chlorine is that. Explain which one has been oxidized. Now we know, hopefully, okay, from oil rig, that oxidation is loss of electrons. Okay, now in this case, the Br minus has become Br2. Okay, so the bromide ion has become bromine. And in doing this, okay, 2 of these bad boys have given out 2 electrons. That means they have, the bromide ions have lost electrons. So the answer there, just to clarify, is bromide. Right, this question is about oxygen, it says. Okay, it says the percentage of oxygen in today's atmosphere is greater than the percentage of oxygen in the Earth's early atmosphere. Explain what caused this to happen. Now, what you're going to say here, essentially, let's keep this simple. It's not a biology exam. You're going to say plants, okay, produce oxygen by photosynthesis. I can write it down here, if that's okay. Try and get it all on one line if you can. Now, magnesium reacts with oxygen from the air to form magnesium oxide. There's a big method there. Explain how the student could check the magnesium oxide had completely reacted with oxygen. Now, what you're going to do essentially is you're going to reheat it and check the mass, okay? Because obviously, if it's completely reacted, the mass isn't going to change. Okay, so you're going to reheat it and check the mass until the mass remains constant. Wonderful. Now, where are we? We are on this one. Oh, I'm going to drag it across. This is looking like a blank page. I like a blank page. And this is looking very much like a mathsy question. It is saying that in another experiment, it was found that 1.24 grams of phosphorus reacted completely with 1.6 grams of oxygen to form phosphorus oxide. The relative formula mass of phosphorus oxide is 284. Deduce the molecular formula of the phosphorus oxide. Okay, now, what we need to do there, okay, is first of all, we're going to find out the number of moles of these things. So we've got 1.24 of phosphorus. 1.24, we're going to divide that by the relative formula mass, or the relative atomic mass, in this case, which is 31. That gives us 0.04. We're going to do the same for oxygen. 1.6 divided by 16. Now that, for the mathematicians among us, obviously is going to give us 0.1. Okay, so we're going to get a mark for doing that. You're going to work out essentially the number of moles of this. Okay, now, the ratio, therefore, would be 2 to 5. Okay, our ratio here, essentially, is going to be 2 to 5. Okay, that is the ratio of things we have, 2 to 5. Okay, now that would therefore give us the empirical formula of P2O5. If it's, 2 P's for every 5 O's, we've got the empirical P2O5. Okay, now you can work out the MR, or relative formula mass, of P2O5 by doing 31 times 2 plus 16 times 5, and that gives you, so my calculator very reliably tells me, 142. Okay, now what relationship does 142 have to this mass of the oxide? Well, it's half of it, isn't it? So therefore, your molecular formula here is actually P4O10. Okay, now please note, you get 1 mark for this, 1 mark for this, 1 mark for working this out, and 1 mark for working this out. Okay, now you aren't allowed error carried forward from errors with ratios, so it's always worth having a go. Now, question D, I'm currently getting grief on my OBS Twitch stream for not playing Minecraft. I do apologise. Anyway, question DI says, explain the change that would be seen after a few days if you left some wet iron wool in a test tube. Okay, well, quite obviously, the iron will turn orange because it has rusted. Okay, now explain one change you can make to the apparatus to allow the student to calculate percentage of oxygen in the atmosphere. Very simply, you need some readings. Okay, so you're going to change the test tube into a measuring cylinder. So you can actually record the volume of oxygen used up. Record volume of oxygen used up. That's what you're going to do. Nice. Okay, we are now on our very last row of pages. Let's try and scroll down there without completely... okay, let's try and scroll down there, he says, without completely destroying the arrangement of the documents. There's a very small chance to grab the whiteboard itself and not the page. Hang on, they're now moaning about posture check, but obviously they can't see me because there's no camera. I promise I am sitting up straight while I'm going through this paper. Now, it says in some chemical reactions, bonds are broken, okay, in the reactant molecules, and new bonds are formed to make the product molecules. Now, which one there is correct? Now, obviously, when you break a bond, you've got to put energy in. Okay, so energy is absorbed. Now, when a bond is formed, therefore, energy will be released. So there's only one correct answer there. It's got to be C. Okay. Now, it says, oh, we love these. It says hydrogen reacts with fluorine. Calculate the enthalpy change to this reaction. Right, so let's work through this methodically. We've essentially got, we've got a HH and we've got an FF. Those are the two we have. And they make 2 HF. Okay, so what we've got there essentially is 436 plus 158. And over here we've got 562 times 2. Okay, 562 plus 562. Okay, so we get 1, this is a 4 marker here, so we get 1 mark for saying our energy in here, which is, as my calculator is very reliably telling me, 594. 1 mark for that. Okay, 1 mark for saying energy out, and this one is 1124. You then do in minus out, that's your 3rd mark, okay? And then your final value will be minus 530. Easy peasy if you know how, okay? Try to learn how. 4 marks actually is quite reasonable. You can always remember, if you get the first 2 wrong, you can still get error carried forward by taking your in number from in number minus out number. If you've written this one as 1 and this one as 2, if you do 1 minus 2, you'll still get that mark, which is quite reasonable. Now, I remember this question from last year now. The memories are flooding back, okay? This was, I would say, without a doubt, the worst 6-mark question I have ever seen. Okay, now, the reason for this, and I'll say this, to score above 2 marks, you have to be able to identify a catalyzed reaction, a reaction that uses a catalyst. Okay, if you don't know a reaction that uses a catalyst, you are stuck in level 1, getting 1 to 2 marks, because you can describe the role of a catalyst, but obviously without identifying a reaction that uses one, you cannot get more than 2 marks, which I think is a little bit harsh, just from me. Now let's go right ahead and let's assume we know a catalyzed reaction, and let's bash through this very quickly. So we're going to go with the Haber process. I like the Haber process. Literally everything I do revolves around the Haber process. Okay, I like the Haber process, and as we know, that is N2 plus 3H2 gives you, we're going to use a reversible reaction because it's a reversible one, 2NH3. Okay, that's that. Okay, that's the Haber process. We don't need that for the equation, other than the question, other than the fact that the Haber process has an iron catalyst. Okay, so that in itself, okay, that in itself, that 2 lines will give you 2 marks. Okay, that's enough to get 2 marks, and it's enough to give you the level 3 marking point, identify at least 1 catalyzed reaction. Okay, you've now got to give a good description of what a catalyst does. Okay, which means it affects the rate of, it increases the rate of reaction without being used up. Okay, oh, I'm wandering off there. Without being used up. That's what a catalyst does. Okay, it affects the rate of, increases the rate of reaction without being used up. Now, the final 2 marks there. Okay, so you're going to get 2 for this. You're going to get 2 for this. Okay, if you'd just written that, you'd be in the 4. Now, the final one is for, like, how does it do that? Okay, essentially, it provides an alternative. No, there's an I in there. Alternative pathway with a lower activation energy. Okay, that's what it does. That's how it does it. That's the last 2 marks, that is. So if you've written those points as bullet points, you don't have to write sentences, okay? Bullet point, bullet point, bullet point. Let's be honest, ask yourself this. That is essentially 6 lines of content, isn't it? You could fit that on this page and you'd get 6 marks for it, okay? Now, I think, although that's a very tricky one because you've got to be able to identify the catalyst first. Now, that is the end of the paper. If you've written everything I've written on there, you would get 100%, okay, which is obviously brilliant. The exam board, had you done this in a real thing, would probably be a little bit suspicious, but we won't go there. We're just going to make sure we learn our lessons from this and go through this. You can pause it, you can answer the questions yourself, you can wait for me to start going on about it. It's all good, okay? Thank you very much for watching, guys, and I will make another one of these very soon.